Hello and welcome back. Recall last time we derived these 5 equations necessary or that govern the motion for an object that is in a state of constant acceleration. And I gave you a heads up that we would be tailoring these equations to a specific case for an object, and that is free fall. So free fall is the condition in which only Earth's gravity exerts a force on an object. No other entity is exerting a force on the object except for Earth's gravity. When this is true, the object is in a state of free fall. So anytime henceforward I say free fall, you know that the only force acting on the object is the Earth's gravity, the pull from the Earth. So the Earth is always trying to pull things vertically downward into its core, and the rate at which objects experience an acceleration or change their velocity is the same for all objects when they're in a state of free fall. So remember that acceleration is a change in velocity over a change in time. And when an object is near the Earth's surface and it's in a state of free fall, then the acceleration for the object in free fall is going to be equal to minus 9.80 meters per second squared. Now, first of all, what does this negative sign mean? Well, the negative sign means that we are calling downward negative. So the acceleration is pointing downward, as is the force of gravity. And acceleration is a change in velocity over change in time. So let's write this a little bit different, see if we can reason this out, have it make more sense for us. So this is going to be minus 9.80 meters per second every 1 second. This is exactly the same thing, just splitting up the units a little bit. So that means that an object's velocity will become more negative by 9.80 meters per second every single second that it is in a state of free fall. We use the symbol little g to keep track of that number 9.80 meters per second squared. So the acceleration of an object in free fall is going to be equal to minus g. Again, the minus sign comes from calling downward negative. Physicists that work with projectile motion, free fall, a lot, sometimes will call downward positive and upward negative. And in that case, then they would just be saying that the acceleration is g. So be careful. This negative sign comes from us calling downward negative. G is just some number. It never gets a negative. G is defined as a positive 9.80 meters per second squared. Whether we define the acceleration as positive or negative g depends on our coordinate system. But we're calling downward negative, and let's just stick with that for the rest of the class. So the acceleration due to Earth's gravity is going to be written as a negative 9.80 meters per second squared. If we round the acceleration in free fall to approximately minus 10 meters per second squared, because 9.80 is very close to 10, it's going to help us do a little thought experiment. So remember, this is the change in the velocity over the change in time. So the velocity is becoming more negative by about 10 meters per second every single second that it's in free fall. All right, so if I throw my pen up in the air so that it leaves my hand with an initial velocity upward of 10 meters per second. I throw my pen up, it leaves contact with my hand at a speed upward at 10 meters per second. Once it leaves my hand, the only entity acting on it is Earth's gravity. And so that means that its velocity should become more negative by 10 meters per second every single second. So it leaves my hand with a positive 10 meters per second in velocity. 1 second later, in order to have become more negative by 10 meters per second, it must be at a velocity of 0. The next second, it has to become more negative still by 10 meters per second. So that means it would be traveling downward then, starting at 0, traveling downward at 10 meters per second. So what if an object is released, let's say, from a helicopter that is at rest, up hovering in the sky somewhere, and I'm up there and I release my pen from rest. In other words, I just simply let go of it. I don't give it some initial velocity down or some initial velocity up. I just simply release the object so its initial velocity is 0. How fast is it moving after 1 second? Well, again, the acceleration in free fall means that the velocity has to become more negative by 10 meters per second every successive second that the object is in free fall. So if it starts off with a velocity of 0, after 1 second, in order to become more negative, it must be traveling at negative 10 meters per second. What about after the second second? So this is object released from rest. So the initial velocity is 0. What's the velocity, let's say, in entering free fall? Entering free fall. Okay, so the initial velocity at time t equals 0 is going to be 0. What about at t equals 1 second? Well, the velocity has to have become more negative from 0 by 10 meters per second over that 1 second. So then the velocity at 1 second is going to be minus 10 meters per second. What about at time equals 2 seconds? Well, it has to have become more negative in this 1 second by 10 meters per second. So that means the velocity at 2 seconds is going to be minus 20 meters per second. What about at 3 seconds? Well, the velocity has to have become more negative by 10 meters per second in that second between 2 and 3. So that means the velocity then is going to be minus 30 meters per second, et cetera, et cetera, et cetera. It has to become more negative by 10 meters per second every single second that it's in free fall. Remember, 10 meters per second is rounding. It's really 9.80 that we're going to be using. But for the purposes of this discussion, it's much easier to work in multiples of 10. So this is how objects behave in the presence of only Earth's gravity and nothing else. So state of constant acceleration. Now what I'd like to do is take these equations that we've written for constant acceleration, and every place we see an a, let's substitute in minus g into these equations. And then the other thing I want to do is when we're dealing with the vertical dimension, which is the acceleration, the direction along which the acceleration is going to lie, right? It's on a vertical axis. Then we usually use the coordinate y. So I'm going to let delta x go to delta y, and I'm also going to let a go to minus g. And I'm going to rewrite these 5 equations up here on the top, tailored specifically for free fall. So these are equations for constant acceleration, tailored to free fall. Okay, so these two substitutions are going to be made, but other than that, the equations are going to remain exactly as they are. So equation 1, what does it become? V is unchanged, V naught. And now wherever I see an A, I'm going to plug in a minus G. So plus a minus is going to give me a minus GT. Okay? So if I know the final velocity and the initial velocity, then using this equation, I would plug in 9.80 for G. I would not be very careful. G is a positive 9.80. The minus sign comes from the fact that we're calling downward negative. So we're saying the acceleration is minus G. So we've already put in the negative sign. We've already put in the negative sign here. What about equation 2? Well, equation 2, here's delta x, but we're going to write that as delta y because, again, it's traditional to use y when you're dealing with the vertical axes. So this delta y over t is equal to v plus v naught over 2. So there's the second equation that's good for free fall. Third equation, delta y, whoops, let's label that as the third equation so that you can see above and below. So the third equation is going to be delta y is equal to v naught t. And now I'm going to have a minus g plugged in for a and this plus sign, and the minus sign is going to give me an overall minus 1/2 gt squared. Equation 4 is going to become delta y is equal to vt. And now I'm going to plug in a minus g for a, so this negative sign that's going to be in front of the g and this negative sign is going to give me a plus 1/2 gt squared. And the last equation, 5, is going to be v squared is equal to v naught squared. And then again, plugging in a minus sign, or the minus g for a is going to give me a plus and minus, which is minus 2g delta y. So these 5 equations using g equals 9.80 meters per second squared gives you the set of equations for constant acceleration, but now tailored specifically to free fall near the Earth's surface, where the rate at which objects change their velocity is 9.80 meters per second squared, and we are giving a negative sign to that acceleration because it is pointing downward, and our coordinate system is going to say that downward is negative. So there we go. These equations now tailored to free fall. So next time we'll do a little bit of practice with this stuff and work some problems.